Okay, now on to our second example of inequalities involving absolute values. And suppose we're asked to solve the inequality, the absolute value of x minus 3 over x greater than or equal to 4. Now, according to our chart, or our above analysis, this corresponds to actually this fourth, the last line, and so the solution set to this inequality is the set of all x so that a, which is x minus 3 over x, is less than or equal to negative 4, or the set of all x so that x minus 3 over x is greater than or equal to 4. So it's going to be the solution, the union of the solutions to these two inequalities. So let's write down these two inequalities. We either have x minus 3 over x is less than or equal to minus 4, or x minus 3 over x is greater than or equal to 4. And now we solve these two separately, and we take the union of their solutions. So let's work on this one. We can convert this to a rational function by bringing this minus 4 over to the left, and we can convert it to a problem where we have to decide where a rational function is positive or negative. So let's bring everything over to the left. That's adding 4 to both sides. We get x minus 3 over x plus 4 less than or equal to 0. Now we have to add these two fractions. 4 is 4 over 1. Looking for our common denominator, it's x. We have x minus 3 over x plus 4x over x. So that's plus 4x there. And we have to figure out where that quantity is less than or equal to 0. So we tidy it up a little bit. We have x plus 4x is 5x minus 3 over x less than or equal to 0. And now remember, we factor, so I'll pull that 5 out, and I get x, 5 times x minus 3 over 5 over x, and I have to figure out where that's less than or equal to 0. I take each factor and I figure out where it's equal to 0. So my factors are x minus 3 over 5, 5, and x, and they equal 0. X minus 3 over 5 equals 0 at 3 over 5. 5 never equals 0, and x equals 0 when x equals 0. Then I find the intervals. This divides the real line up into a bunch of connected intervals. So the points of interest are 0 and 3 over 5. And my intervals, my set of intervals, are from minus infinity to 0, 0 to 3 over 5, and 3 over 5 to infinity. And remember that this rational function maintains the same sign on each of these intervals. So I have my three factors, and I have to figure out whether they're positive, negative, or 0. Well, just positive or negative on all of these intervals. 5 is obviously positive everywhere because it's a constant. It doesn't change as x changes. X minus 3 over 5 is positive when x is bigger than 3 over 5, and negative when x is less than 3 over 5. And x itself is going to be positive when x is bigger than 0, negative when x is less than 0. Then finally, my rational function, 5 times x minus 3 over 5 over x, it's a combination here of two negatives and a plus, so I have an even number of negative factors, so it's going to be positive there. An odd number of negative factors here gives me a negative, and they're all positive here, so I get a positive. And I'm interested in knowing when this rational function is less than or equal to 0. And so that happens somewhere between 0 and 3 over 5. For everything between 0 and 3 over 5, strictly between, this is less than 0. And it's actually equal to 0 when x is 3 over 5. And when x is 0, it's not defined. So I don't include that in my solution set. So my solution set to this equation on the left is the interval from 0 to 3 over 5, including 3 over 5. Now that's the solution set to one of these inequalities. Recall that I have to get the solution set to this one, which I found, and take the union of that with the solution set of this one in order to find the full solution set to this original inequality. So now we work on the solution set to this inequality. Again, the same approach works. We convert it to an inequality involving a rational function by bringing everything over to the left, every non-zero term, and then we have to figure out where that rational function is positive or negative. So we have x minus 3 over x minus 4 greater than or equal to 0. I have to decide when that happens. So again, I have to add these two fractions. So the common denominator here is x, so we have x minus 3, 1 into x goes x times minus 4x greater than or equal to 0. So my question is, when does that happen? For which x values does that happen? Well, I'm going to tidy up. X minus 4x is minus 3x. And I want to decide when minus 3x over x is greater than or equal to 0. I pull out that minus 3, and that gives me 1 plus x there over x greater than or equal to 0. Okay, now I have three factors. Minus 3, 1 plus x, and x. And they're equal to 0. Well, this one never. This one's equal to 0 when x equals minus 1. And this one equals 0 when x equals 0. Now I figure out which intervals. Remember, if this quantity changes sign, it must be at one of these 2 points. So these 2 points split the real line into 3 intervals, and the sign of this rational function remains constant on all of those 3 intervals. So these are my intervals, and I have to figure out the sign of each factor. Sign of minus 3 is always negative. The sign of 1 plus x is going to be positive for x bigger than negative 1 and negative for x less than negative 1. And the sign of x is going to be positive for x bigger than 0, negative for x less than 0. And now the sign of my rational function here, minus 3, 1 plus x over x, this is a combination of 2 pluses, 1 negative. There's an odd number of negatives, so it's going to be negative. An even number of negatives here, so it's going to be positive, and an odd number of negatives here. And I'm looking for the x values for which minus 3 by 1 plus x over x is greater than or equal to 0. Well, it's going to be greater than 0 in this interval between minus 1 and 0. And we're also interested in the points where it's equal to 0, and that's for x equals minus 1. And this thing is undefined for x equals 0, so that's my solution set there. So the solution set, this is true for x in this interval. Okay, so that's my solution set to this inequality. And now recall, that the solution set to this inequality is the union of the solution sets to these two inequalities below. So the solution set to the one on the left we figured out was everything from 0 to 3 over 5. And it's all of that along with all of the x values which satisfy the second inequality, and that solution set we saw was everything from -1 to 0. And so that gives us our solution set to the original inequality.